What a zonerism means, if you can take a fact and then be totally misled to the false conclusion. You have to be able to ask questions, you have to be critical thinkers. Because if you have a bad analysis, you're going to have bad remedies. You got to be critical thinkers and know that we are easily fooled. And that's why you have to have debate. You have to have people discuss it, because sometimes we might not see how we're fooling ourselves.
This episode is the second part of our interview with biologist and CO2 Coalition Director Jim Steele.
Jim, we're hearing a lot of concern about an increase in ocean temperature. Can you lend some expertise to this concern?
I can hit it from a couple of point of views. And to me, what is amazing is people say CO2 is trapping heat. Well, CO2 will absorb infrared heat and it will release it again in 1/100th of a second, 1,000th of a second. So it doesn't really trap it. It just delays its outgo. And the real places that heat is being trapped is in the oceans. And the best way I've tried to explain this to different groups is to look at solar pond dynamics. And solar ponds are being studied as a way of inexpensively heating different buildings. In University of El Paso, Israelis, a few places have really been studying it. And so what you see here is a typical solar pond. It's about 10 feet deep and it's characterized by 3 layers. The upper layer, you have the freshest water, the less dense, and that's the most buoyant. It floats on the top. And any heating there can be convected later in the day or through the night and be released, or maybe later in the season. The key is what's called the storage zone of the solar pond, and this is where you make the water very salty and very dense. And so when the sun heats that layer, even though it's warmer, and you would think warming waters would float to the top, the salt makes it so dense it's stuck at the bottom. And the heat accumulates. This is where heat is truly trapped. And now you can get temperatures up to 90 degrees centigrade. And it's enough that they'll pipe that to buildings and to keep them warm. So you just have to maintain these 3 layers, and you have a transition, an insulation zone that's a little saltier than the freshwater surface, but a little fresher than the bottom. And so that kind of protects the heat from rising to the surface. So sometimes it's the heat that happens in the ocean over a whole year. It might take a couple of years for that heat to work its way up. This solar pond dynamic is almost identical to what we're seeing in the Arctic Ocean. You have fresh water at the surface zone that would be from melting ice or river inflow or rains. You have warm Atlantic water. The water is heated in the tropics and then carried by the Gulf Stream and other currents into the Arctic Ocean. But it is so salty, even though it's warmer, it's trapped in the lower layers. You have a layer of this warm Atlantic water. It's 100 to 900 meters depth. And it doesn't make the surface, the air temperature any warmer, because the only way for that heat to get out, it has to get to the surface. And you have this insulation zone that scientists call the halocline. It's a little fresher than the Atlantic water, but it's a little denser than the top part. For 40 years, scientists were studying the temperature over the Arctic Ocean. And they published in 1993 in one of the top journals that there was no evidence of global warming in the Arctic Ocean. They just didn't see it. And then you had something called the Arctic Oscillation that changed the winds and changed how much fresh water kept that insulation zone, the halocline, working. And so you started seeing a number of papers saying there was a retreat of the halocline. And this was allowing that warm Atlantic water to come closer to the surface. So as this hot water, or relatively hot water in the Atlantic is escaping, it warms the air surface above it. So the Arctic isn't warming because of CO2, it's warming because the Atlantic water is ventilating its heat more. And actually, it's cooling the whole energy budget for the Earth by ventilating that heat. But because of the way we measure that, the air temperature is up, we say, oh, the global temperature is getting hotter. But it's a total misunderstanding of what's happening. Another important way to look at what's going on in the Arctic Ocean and to see how important this inflow of warm Atlantic water is looking at where the ice is melting the most. And this is from NOAA. It's March when the sea ice is at its maximum annually. And if I insert the Arctic Circle here, we can see most of the Arctic reaches all its ice completely every year except for one place. It's even cold enough for things south of the Arctic Circle where temperatures are warmer, like the Hudson Bay, to get completely frozen over. The one place that the ice is mostly melting is oddly inside the Arctic Circle. And I put this black box, this is the Barents Sea, and this is where most of that warm Atlantic water is flowing in. And if we look at the actual currents, the diagram of the currents, we can see that you have this warm Atlantic water coming in, and it's around the Barents Sea where most of that water is, which is also where you see most of the melting happening in the Arctic. And in the Barents Sea, the temperatures are rising 7 times higher than the average temperature. And so the average is really useless here. And what's causing this higher temperature is this ventilation of heat. And one thing I want to emphasize is location determines your extremes. It was the location that caused my meadow to dry out, not the general climate. The most melting in the Arctic Sea is due to its location where the hot water is coming in. Well, here is a study that looked at where the most extreme rainfall was happening. And if it's blank, they haven't had any extreme rainfall. So most of the country isn't that suffering extremes. You see the purple dots and the light blue dots say you've had extreme rainfalls once to twice over the 40 years that they were doing this study. And if you look at all the dots in the eastern United States, that's where temperatures have been cooling. And the reason why they're getting extreme rainfall is that location is where a lot of the hurricanes land. The place where you get the most repeat extreme rainfall happens in California. It happens right about where I was doing all my research, and you can see that by the red dots. And this is due to 2 things. It's the way El Niño and La Niña brings in a lot of moisture, and the way another event called atmospheric rivers bring in a lot of moisture. And they're the ones that control the extreme rainfall and create what we might call mega floods.
Jim, which recent extreme weather event best shows natural patterns like El Niño, La Niña, or atmospheric rivers driving floods or droughts, not CO2?
One thing you can see is the way you have these patterns alternate. El Niño and La Niña conditions alternate every 3 to 7 years. But if I look at this picture of what a La Niña is, it's really sort of the natural condition in the Pacific. And the trade winds blow all this warm water over to the Western Pacific. And that's where you get the heavy rainfalls for the monsoons in Asia, Northern Australia, Indonesia, in that region. And the warmer water causes all this rising convection in that region. And then in the upper air, it finally converges in the Pacific here. It comes down in the Eastern Pacific, just off the coast of California. And so what my first experience was this: in 1998, we had a large El Nino. The bridge to my field station got washed out, and tremendous snowfall. Some of the birds didn't even go to the higher country because it was just too much snow for them. But at the same time, there was droughts in Indonesia. So El Nino will turn you one way, La Nina will push it a different way. And the other thing, again, we talk about how heat is trapped. All this water going in a La Nina-like condition, it can get stored up to 200 meters below the surface. And it doesn't get released until you have an El Nino. And then this is what doesn't get pushed enough is what we call teleconnections. When you have this rising convection, you excite the atmosphere in a way with energy waves where you cause what they call a Rossby wave train, where you get alternating high and low pressure systems. The rising convection is a low pressure system, but it can cause it to go across the Pacific. And then in Argentina, you can also have heavy rains. And then further up the north in Brazil, you have a high pressure causing a drought. So this El Nino, La Nina, it's happening in the Pacific, but it's getting transmitted all around the world. So if you look at what's happening around the world, we can predict during a La Nina-like conditions what areas are going to likely get the most rain. So in a La Nina, it's mostly around Indonesia, Eastern Australia. You also get some in sub-Sahara Africa, South Africa. In Brazil, the Amazon gets a lot of rainfall. The rivers run at their highest length. But in the United States, the southern United States is very dry. And the final thing, just to push, and there's a little more complexities, but La Ninas tend to disrupt the jet stream, and it causes it to become even more wavier. And so it pushes the moisture that's coming off the Pacific further north, and then the jet stream dives down, which is why you're getting the real cold weather you have in back east. Is as its jet stream dips down, it's pulling cold water further south, cold air further south. It's the trade winds that help keep all that warm water stored in the Western Pacific during La Nina events. But when there's a disruption to the trade winds, you get a burst of wind from the west, it causes all this warm water that had been stored to flow across the Pacific. And it can stop in different places, so it's not always going to cause the exact same effect. But what you do is you shift, or what it does, it shifts the center of convection to the eastern or central part of the Pacific. And that changes the wave trains, or where the high and low pressures are being transmitted across the country. And because of these wave trains and the way these teleconnections work, when you have wet in southern United States, you have very dry in eastern Australia, Indonesia. You have dry in India, and you get droughts in India, where maybe in Pakistan further it would be wetter. And you have in the Amazon, you have very dry conditions. And I just saw something by Al Gore saying, the rivers in the Amazon are drying up due to CO2 warming. And it has nothing to do with it. It was a La Nina that was causing the rivers to go down. And it's been studied for 100 years because of the way river transports go, is you can connect when the rivers are low and the rivers are high due to El Niño and La Niña. There'll be some other things that add to it, but that's the principal reason for why you get these patterns around the world. When you have an El Niño-like conditions, the jet stream isn't as wavy, but it kind of moves a little further south. So that's what brings all this wetness to the southern United States. It's not because the air is holding more water, it's because more water is being transported into the United States by the jet stream. And to just finish on, there was a great drought and famine in 1876. Nearly 50 million deaths are estimated. And it was related to an El Niño event that then was transmitted all around the world. So in an El Niño, you have a dry Eastern Australia, you had drought there. You had drought in India, you had drought in the Amazon. And in India and Pakistan, they had probably about 7 million deaths. But this was not because the air was warmer or because there was more CO2. This was in 1876 when temperatures were low and CO2 was low.
You call the idea that warmer air holding more moisture directly causes more floods another zonerism. Why do you see atmospheric rivers as the real main driver of most extreme rainfall and flooding events?
Well, I can show you several examples. And here I've put something up for the United States National Weather Service. And it measures how much moisture is in the air. And typically it's in the tropics where the trade winds converge and they bring all this moisture together and it rises. So the light blue in this graphic is where you have a tremendous amount of moisture. And there's numbers that they can measure how much is there. You can also see each hemisphere will have 3 to 4 atmospheric rivers emanating from that convergence zone. And depending where those rivers hit is where you're going to get rains that are extreme. And if those rivers are guided by low and high pressure systems, those pressure systems stay sort of static in one place, you can have these atmospheric rivers focus for 30, 40 days. But when that happens is when you get these mega floods, not because of warmer air temperature, but because of the transport of moisture. So if you look in this one, right, you see there's no moisture being transported to the Sahara, even though it has hot temperatures, but you have a tremendous amount of moisture going to Scotland and Great Britain and to California. And the most obvious, and here in California, I'm very sensitive to these atmospheric rivers, these mega floods. Well, when did they happen? The last mega flood in California happened in 1862. It flooded the Sacramento Valley. The real estate maps caused the central California to be a marshland. The state capital is in Sacramento. They had to abandon and move to San Francisco because there was such high water. They got 35 inches in 40 days. And again, 1862 is the end of the ice age. It's colder. There's lower CO2. It has nothing to do with warmer air holding more moisture. But that's the zoner. Every time someone asks, why did we get this flood? They say, well, global warming causes the air to hold more moisture. But it has nothing to do with it. The Sahara doesn't get more moisture. It depends on how these rivers are moving. And we can study the sediments in places that have been undisturbed and see how every year you have more rain or less rain. And what they just found out, it was about a decade or so ago, looking at the coming mega floods, that California gets a mega flood almost every 100 to 200 years. So you had the 1862, we've had it in the 1700s, in the heart of the Little Ice Age, 1600s. These all have nothing to do with warmer air, but the way moisture gets transported. And if we want to look at what's going on in California precipitation-wise versus natural variability, John Christie did this map of looking at rainfall in the Sierra, and you see it varies widely. So some years you're going to get some heavy rain, some years you're going to get droughts. It all has to do with how you have El Niño, La Niña, and atmospheric rivers bringing moisture to California. The last, this transport of moisture is what's going to make a certain location more vulnerable to wildfires and others less so. The way the pressure systems work in the Pacific, they block a lot of the water from coming to the western United States, and the mountains also create a rain shadow. But in California, it doesn't rain in the summer. I came from Boston where you got tons of rain in the summer. It blew my mind not to see any rainfall in California because the way this pressure system blocks the transport of moisture. So the West gets very dry, and it is the place that's most susceptible to wildfires. In contrast to the eastern United States, the pressure systems now are pumping a loss of moisture from the Gulf of Mexico. So the eastern United States has high humidity. And you have very few fires that are happening relative to the western United States. In the United States, 90% of the fires are started by humans. So that makes another variable that people don't really talk about. So in California, where I was working, there's a number of places near me that had some extreme fires. And some of this dry conditions also affects the vegetation. So if you talk about what you have to start a fire, start a campfire, you don't light a match and hold it under a log. It doesn't have enough sustained heat to do that. What you have to do is have some tinder and some kindling that can sustain enough heat that then it can light a log. Now, what fire experts talk about is your tinder is like dry grasses, and kindling is like dry shrub twigs. They call them 1 hour and 10-hour fuels. What that means, in one day of dry weather, the tinder in a kindling is highly flammable. And that makes climate change totally irrelevant. And what I saw after we had this fire in the Pacific Palisades down in LA, you had Michael Mann coming out and saying, oh, it's global warming, it dries the vegetation. Well, that's a zonerism, because what you have is, yes, things dry out quicker if it's warmer, but it only takes 1 or 2 days to dry this. Climate change is a 30-year change, so global warming has nothing to do with it. And that's why a lot of these fires are due to bad land management, because when they start suppressing fires, they cause the tinder and the kindling to accumulate. So when it finally got ignited, it caused bigger and hotter fires. There's been some, what I think are very dishonest talk about global warming because it's drying out the vegetation is making wildfires worse. But if you look at the historical changes in wildfire, you see there's been a little bit of an increase since 1970, but it's dishonest to portray it that way because what we had since the beginning of like 1900 was people were concerned about fires eliminating too much forest, about burning buildings. So there was a whole campaign of fire suppression. And that continued until about the 70s when ecologists started learning, well, that fires were natural. We know there's a number of plants that are totally adapted to fire regimes, that when you don't have enough fires, the kindling and tinder start to build up, and then that allows some bigger fires. So starting around 1970 is the Forest Service and CAL FIRE, they started adopting a policy of if there's no threat to a building, let it burn. Where before the Forest Service said if we see a fire, we want it out by 10 a.m. the next day. So they relaxed all that. So that's allowed a little bit of an increase in fires. And you can see this in the history of fires in Oregon, that there were a lot more fires there in the 1930s and before, and then they were totally suppressed. And then there's a little bit that have come back since the 70s. And what's more striking, studies have looked at the whole southwestern part of the United States. In the 1700s and 1800s, when temperatures were far cooler, when there's far less CO2, you had the most fires, far more. And then around 1900, as fire suppression set in, you went down to hardly any fires whatsoever because they put them out right away. So if you understand the history and you understand how the vegetation operates in allowing fires to happen, it's not because of CO2 or it's not because of global warming causing drier vegetation. That's happening naturally. It's about how we manage the land. And so it's landscape changes that are really the big issue.
Jim, as a lifelong environmentalist, what's the key takeaway you hope listeners get from your journey, and what can they learn from zonerism?
Realize what a zonerism means is you can take a fact and then be totally misled to the false conclusion. So you have to be aware that in asking critical thinking. One of my favorite scientists says is, skepticism is our highest of duties. And if you have to be able to ask questions, you have to be critical thinkers. Because if you have a bad analysis, you're going to have bad remedies. And if you waste money trying to go to net zero or something like that, instead of dealing with the landscape changes that are really causing these extremes, you're not solving the problem. So you got to be critical thinkers and know that we are easily fooled. And that's why you have to have debate. You have to have people discuss it, because sometimes we might not see how we're fooling ourselves.
Jim, it's been such a pleasure having you on Climate Debrief. We hope to have you again soon.
Well, thank you so much for having me. It's always a pleasure to talk with you, Angela.
Thank you for watching. The Climate Debrief podcast is funded by listeners like you. If you enjoyed listening to this episode of Climate Debrief, please like, comment, and subscribe. We read all of your feedback. If you are interested in finding out more about the CO2 Coalition and its mission, visit our website at co2coalition.org. Our host and executive producer is Angela Wheeler. Production by Ethan Audie and Scott Wheeler. Technical production and editing by Joseph von Spakovsky.